Good day, everybody. Today I want to look at a special function that's defined using an improper integral, and it's essentially the gamma function, but I'm going to use Gauss's version. He calls it pi of n. So it's defined as the integral from 0 to infinity of x to the n e to the negative x dx. So you're going to integrate out x, and then it'll change depending on n. So n is kind of the variable here. For starters, let's look at pi of 0. So if I plug 0 in, x to the 0 will be 1. So I'll just have to integrate from 0 to infinity e to the negative x. And it's a pretty easy integral to do if we do it rigorously with our improper integral knowledge. We just have to evaluate basically e to the negative infinity will be 0, and then minus a negative e to the 0, which will be plus 1. Let's look at if we plug 1 in for n. So pi of 1 will be integral 0 to infinity x to the 1, or just x, e to the negative x. So now I will have to integrate by parts. So we'll let u equal x, du will be dx, dv will be e to the negative x dx, v will be the negative of e to the negative x. And so the integral will be uv, which will be x times e to the negative x, negative e to the negative x. And I'll put the e to the negative x in the denominator as e to the x. And then we'll evaluate from 0 to infinity, or limit as b goes to infinity. And this will be 0 in both cases. So if the numerator goes to infinity, but the exponential goes to infinity so much faster that the limit of this fraction is 0. And then when you plug in 0, you get 0 over 1. So that's 0. We get minus the integral of v du, but v has a negative. The two negatives make a plus. And then we get this integral. And this integral is the previous integral, which was 1. So maybe we see a pattern, but let's not jump to conclusions yet. So let's look, if I plug 2 in for n, so now it'll be x squared e to the negative x for my integrand. Then I've got that integral. Again, I'll have to integrate by parts. U will be x squared, du will be 2x dx, dv is going to be, once again, e to the negative x, so v will be negative e to the negative x. So we get uv, which I'll write this way, minus the integral of v du. Now v du is again minus a negative, so plus, and then I got 2x, I'll pull the 2 out. And then as b goes to infinity, again, you could use L'Hopital's rule, the numerator doesn't go to infinity as fast as the denominator. This fraction will go to 0. So that'll go to 0, and then if you plug in 0, you'll get 0 over 1. And then this will be 2 times the previous integral. So that'll be 2 times 1. And that's really the pattern. I'll do it one more time here. If I plug 3 in for n, so it's x cubed e to the negative x for my integrand. Again, I'll integrate by parts. Du will be 3x squared dx. dv and v the same as before. So uv, and they'll both go to 0. And then minus the integral of v du. So that'll be minus a negative, and then I have 3x squared. So it'll be plus 3 times the previous integral. So 3 times the previous integral is 3 times 2. And that's the pattern. That's going to be n times the previous result, which is like the factorial. In fact, if we do pi of p as the integral of 0 to infinity x to the p e to the negative x dx for p greater than negative 1, because you should know for improper integrals, 1 over x to the p will converge on this integral 0 to 1 if p is less than 1. And for this improper integral, any power growth will be dominated by this exponential decay, and you'll converge on the infinity side. On the 0 side, e is going to approach 1, so you're roughly like 1 as you get closer to 0. So you need 1 x to the p to converge. And that's what we will have if, well, in this form, if p is less than 1, and that's equivalent to this, 1 over x to the p is x to the negative p. But if I write it as x to the p, then that means I need negative p less than 1 or p greater than negative 1. Right, so this integral converges, I guess, if and only if p is greater than negative 1. Okay, so this integral will converge for p greater than negative 1. Now I'm going to get a recurrence relation. For that, I'm going to look at for p greater than 0, we would have for this integral, using integration by parts, u equals x to the p, du is p x to the p minus 1, and dv, again, e to the negative x, v negative e to the negative x. So then I get uv, and I'll be okay here if I restrict to p greater than 0. Evaluate at those limits, those will both be 0. And then minus the integral of v du, and again, v du, well, that's a negative, so minus a negative, and then I got that p. So it'll be p pi of p minus 1. So we have this relationship, and this defines the factorial. 0 factorial is 1, n factorial is n times n minus 1 factorial for n greater than or equal to 1. But now I'm going to loosen the restriction that I have to be an integer and just say it's true for the real number. So pi of 0 is 1, and then pi of p is p times pi of p minus 1 for p greater than 0. Looking at the integers, again, we get our recurrence relation. So pi of 0 is 1. I mean, that was done on the first page, and starting point of the definition for the factorial. And then pi of 1 is 1 times pi of 0. Pi of 2 is 2 times pi of 1. Right, so this one's 1 times 1, this one's 2 times 1. Pi of 3 is 3 times pi of 2. So now all I'm doing is just using the recurrence relation. And if you keep doing that, I mean, you, of course, mimic the factorial. And we're actually going to expand the values that we can evaluate at by going in reverse, right? So if pi of p is p times pi of p minus 1, so we saw that relation. Well, I can solve for p minus 1. Pi of p minus 1. Pi of p minus 1 is pi of p divided by p. So let's say we know some value. I started at 4. If we know pi of 4 is 24, then you could get pi of 3. It would be pi of 4 divided by 4. 24 over 4 is 6. And then you could keep going. Pi of 2 is going to be pi of 3 over 3. 6 over 3. Now I know that's 6. Right, so I'm just using that identity. Pi of 1 would be pi of 2 over 2, which I now know that's 2 divided by 2. So that'll be 1. Pi of 0 would be pi of 1 over 1, which I now know is 1 divided by 1. So that's 1. So I get that. Now if I try to go backwards to the negative integers, I run into trouble. Pi of negative 1 would be pi of 0, which is 1, but divided by 0. So that's undefined, and then once you're undefined, you can't recover from that. But we can get pi of 1/2 and pi of negative 1, and in fact pi of any other value. Going back here, right? So I can plug in any real number and have this evaluated numerically. There's one value that's not a positive integer that we know also, and that's the 0.5 values. Starting at, say, pi of negative 1/2, by definition, that would be x to the negative 1/2 e to the negative x, so that integral. And if I do a substitution, u equals root x, that's equivalent to x is u squared, or 2u du is dx. Then the limits, x going from 0 to infinity, will have u going from 0 to infinity as well. So then pi of negative 1/2 is x to the negative 1/2, or 1 over root x, e to the negative x dx, or in terms of u, it'll be u goes from 0 to infinity. This will be 1 over u. This will be e to the negative u squared, and dx is 2u du. The u's cancel, and you get 2 times the integral 0 to infinity e to the negative u squared du. This is an even function, so 2 times this integral is the same as the integral with the symmetric limits, negative infinity to infinity. And this is well known to be root pi. Right? E to the negative u squared won't have an antiderivative in terms of the elementary functions, but we can get the exact value with these infinite limits anyway. So if I know pi of negative 1/2 is root pi, I can work my way forward. Pi of 1/2 is going to be 1/2 pi of negative 1/2, just using this recurrence relation. So I can get pi of 1/2 is 1/2 times pi of negative 1/2. 1/2 minus 1 is negative 1/2. And you can keep going. Pi of 3/2 will be 3/2 pi of 1/2. Right, so this is 1/2 root pi. This is 3/2 times root pi over 2. Pi of 5/2 will be 5/2. Pi of 3/2, which is pi halves, 3/4 root pi, or 15 over 8 root pi, and so on. So we can get all those values. Now we tried going backwards and it didn't work for the integers, but it will work for non-integers. So we already knew pi of negative 1/2 is root pi, but if I start at 1/2 and call that root pi over 2, then I can get it. It's just the value that's 1 before divided by p, right? So the value that's 1 more than negative 1/2 would be 1/2. So it's pi of that value divided by that value. So that's root pi over 2 divided by 1/2, which is root pi. But I can use that recurrence relation to keep going now. Pi of negative 3/2 would be pi of negative 1/2 divided by negative 1/2. Pi of the value 1 before divided by that value. So it'll be root pi divided by negative 1/2. So it'll be negative 2 root pi. And you can keep going. So with the recurrence relation, we can get every value of x except the negative integers. Right? So using this recurrence relation, that it will allow us to go backwards. Now I want to emphasize this integral does not converge though for those new values. We just use something called analytic continuation. Well, that would make it rigorous. I mean, I used a recurrence relation to go backwards, but there's something called analytic continuation, and so that would mean the functions behaves nicely. But even if we can find pi of negative 3/2, that does not mean this integral converges now. We just extended the function. So let's look at some software work here. So there's e to the negative x squared against root pi, as we all know. And again, I can define this factorial function, is kind of what I was calling it here, to be this integral. And then factorial of 0 is 1, and so on. I can do factorial of 6, it would be 720. I can do the negative 1/2, and I get the root pi, or if I want it as a decimal, I'll do 0.5. And if I try to go beyond, that integral is still undefined. So I can't go to the left of negative 1 for the integral. I can plot the function and maybe zoom in. Right, so there's at 0 it's 1, at 1 it's 1, at 2 it's 2, at 3 it's 6, and at 4 it's 24. Those are labeled. A lot of software does accept the factorial function. So here I can plot x factorial and I'm fine. And then it's going to at 24 and 6, that's where it'll be 3, and 4 is up here, and so on. A few interesting facts. The derivative at 0 is negative gamma. So not as well known constant, but a pretty important constant. So that's the derivative at 0, negative gamma. its minimum value. So obviously at 0 it's 1, and at 1 it's 1, and then it dips. So the minimum value, it's not quite at 1/2, it's a little before. Here's the decimal approximation of the value of x, and then the value of the factorial, that's the minimum. So again, it does have a minimum very near 1/2. And again, this function can be extended beyond -1 through that recursive relation, even though the original integral doesn't converge. Now, the more popular version of this function is called the gamma function. So I'll plot that as well. It's the exact same function, but shifted over 1 unit. Well, if you shift the factorial to the right, you get the gamma function. Right, so the factorial has its first vertical asymptote at -1, and gamma has its vertical asymptote at 0. I don't really like the fact that it was shifted by 1. Again, with Gauss version, you have the pi of n is n factorial. With the gamma function, instead of x to the a, it's x to the a minus 1. So instead of gamma of n being n factorial, it's gamma of n plus 1 is n factorial. So that's the only difference. Apparently Legendre named it, and I wouldn't say there's good reason for it. I don't know if we're stuck with it. It seems slightly like we're stuck with it, but Legendre's normalization does simplify a few formulas, but complicates most others. So I don't think it's worth it. This was from the book The Gamma Function by James Bonner, Treasure Trove of Mathematics. All right, so that's the idea, the result. We've got essentially a factorial function. It's going to match the factorial at all the integers, but it's defined for all values on the real line bigger than -1, and then this integral is, but then you can recursively define for all values on the real line except the negative integers. Right, so in case you come across that function, it is pretty useful. So thank you for watching. Have a good rest of your day.